Good morning, everyone. My name is Khushi from Bsc Chemistry Honors, second year, and today my chapter is Ultraviolet Absorption Spectroscopy. Introduction. One of the important fields of activities of an organic chemist is the determination of structure formula of various substances. In earlier days, the structure formula education was mainly based upon the study of classical physical properties like melting point, boiling point, refractive index, etc., and chemical reactions of the compound. The procedure involved was rather laborious and time consuming. However, in the last 50 years and so many particular years, the method is spectroscopic methods, which are based upon the interaction of electromagnetic radiation with the substance under examination. It may involve the study of ultraviolet, infrared, and nuclear magnetic resonance (NMR) and mass spectra. The major advantage of employing these spectroscopic methods for structure determination and identification of substances are as follows. They need very little time, and the information obtained is often a permanent record in the form of a chart. The substance is required in very small quantities of the order of 1 milligram. The methods are extremely sensitive and highly reliable in establishing the structure of compounds and analysis of mixtures of closely related compounds. They can be used for the detection and identification of even short-lived reaction intermediates during the spectroscopy studies. Except mass spectroscopy, the compound is not generally affected chemically and can therefore be recovered unchanged. Continuous analysis is often possible, facilitating the study of reaction rates, etc. In this chapter, we shall deal with the basic aspects of ultraviolet spectroscopy, the electromagnetic spectrum, and spectroscopic studies. Electromagnetic radiation. Many spectroscopic techniques are based upon the interaction of a compound with light or some other form of energy. Electromagnetic radiation. It is well known that the light and other electromagnetic radiation are different forms of energy with a dual character. They have the properties of both a wave and particle. They are known as electromagnetic radiation because they consist of oscillating electric and magnetic fields which are perpendicular to each other and perpendicular to the direction of motion wave. Some important characteristics of these radiations are the energy of these radiations is inversely proportional to their wavelength or directly proportional to their frequency. Second, these radiations do not require any physical medium and can be transmitted through empty space. For example, light reaches us from sun through empty space. All type of electromagnetic radiation travel through space with the same velocity, which is nearly 3 into 10 raised to the power 8 meter per second. Electromagnetic radiations can be described in terms of their characteristics such as wavelength and frequency. Wavelength, it is the distance between two adjacent crests or troughs in a particular wave. It is denoted by lambda. The wavelength is usually expressed in meters, micrometers, nanometers, and angstroms. 1 micrometer is equal to 10 raised to the power minus 6 meter. 1 nanometer is equals to 10 raised to the power minus 9 meter. 1 angstrom is equals to 1 into 10 raised to the power minus 10 meter. Frequency, it is the total number of waves which passes through a point in 1 second. It is denoted by nu. Read as normal. The frequency is generally expressed in cycles per second, CPS, or simply second inverse, or hertz, Hz. The frequency and wavelength are related to each other as nu is equals to c over lambda, where c is the constant velocity of light. Wave number, it is the reciprocal of wavelength and represents the number of waves per centimeter. It is denoted by symbol v. Wave number is generally expressed in centimeter inverse, reciprocal centimeter. Wave number is related to wavelength and frequency. Nu is equals to nu over c. SI unit of wave number is meter inverse. Energy of electromagnetic radiation. Electromagnetic radiations are associated with discrete energy units called quanta or photons. The energy of photon is directly proportional to its frequency or inversely proportional to its wavelength as shown. Energy is equals to h nu. H is equals to c nu is equals to c over lambda, where h is Planck's constant. Electromagnetic spectrum. Visible light which can be detected by human eye consist only a very small part of electromagnetic radiation. The full range of this radiation is indeed very large, and their wavelengths vary from a very small fraction of a meter or to many kilometers. The arrangement of entire range of electromagnetic radiation in increasing order of their wavelength or decreasing order of their frequency is known as electromagnetic spectrum. The complete electromagnetic spectrum is given below. Principle of absorption spectroscopy. It is interesting to note that particularly all the important spectroscopic methods used for structural analysis belong to the field of absorption spectroscopy, which studies the absorption of electromagnetic in relationship to molecular structure. When a beam of electromagnetic radiation is passed through a substance, the radiation may be either absorbed or transmitted depending upon the wavelength of the radiation and molecular structure of substance. Absorption of radiation would naturally bring about an increase in the energy of molecule, the energy gained being directly proportional to the frequency or inversely proportional to the wavelength of radiation. The increase in energy of a molecule may lead to electronic excitation, whereby electrons are raised to higher energy levels. Alternatively, it may be bring about an increase only in the vibrational or rotational energy of the molecule. Electronic excitation can be caused only by high energy radiation such as ultraviolet and visible radiation. On the other hand, vibrational and rotational energy levels can be raised even by relatively low or low energy infrared radiation. A very important condition for a molecule to absorb electromagnetic radiation, that energy of a photon must be equal to the energy difference between the two vibrational, rotational, or electrostatic state. Ultraviolet spectroscopy. Ultraviolet spectroscopy involves the measurement of absorption of light in the visible ultraviolet region. Visible region wavelength 400 to 800 nanometer, UV region 200 to 400 nanometer by the substance under investigation. Since the absorption of light involves the transmission from one electronic level to another within a molecule, UV spectroscopy is also known as electron spectroscopy. Absorption laws. There are two laws in this chapter. The first one is Beer's law. According to this law, when a beam of monochromatic light it passes through a substance dispersed in a non-absorbing solvent, the absorption of light is directly proportional to the molar concentration of the absorbing substance. The second law is Lambert's law. This law states that when a beam of monochromatic light it is passed through the substance, the absorption of light is directly proportional to the path length of the sample of the substance. Third law is Beer's-Lambert's law. The two law states above can be combined to get a general absorption law termed as Beer's-Lambert's law. It may be stated that the absorption of light by a substance at a particular wavelength is proportional to the number of molecules of the substance in the path. Limitations of Beer's-Lambert's law. Its limitations are it is strictly obeyed when dealing with the UV spectra of single species. However, if a sample contains different structural forms of molecules in equilibrium with each other, such in the case of keto-enol tautomers, the law is not obeyed. It is also not applicable if the solute sample or solvent interact with each other to form complexes. Molar absorptivity. It is a proportionality constant which relates the absorbance at a particular wavelength to the molar concentration of the absorbing substance and length of the light in centimeter. The transmittance of sample will be given by the relation T is equals to I by I naught. 100% transmittance is equals to 100 into I by I naught. Mechanisms of recording the UV spectrum. Presentation of the spectrum. Excellent ultraviolet spectrometers are now available which can conveniently record the spectra over the ranges of 200 to 800 nanometer. 200 to 400 nanometer is known as near ultraviolet region, while 400 to 800 nanometer is visible region. Since oxygen of the atmosphere strongly absorbs light at 200 nanometer and below, the uses of wavelengths shorter than 200 nanometer is not practicable unless special vacuum techniques are employed. The ultraviolet spectra are also recorded on wavelength scale in millimicrons, mu, or nanometers. Procedure for recording the ultraviolet spectrum: the given compound is mu or nanometers. Procedure for recording the ultraviolet spectrum: the given compound is generally dissolved in some suitable solvent which does not itself absorb light in the region under examination. The commonly employed solvents are 95% ethanol, hexane, and water. It will light up the tungsten filament lamp. UV spectrometer. A simplified diagram of UV spectrometer is shown below. It consists of the following parts: a source of radiations which emits all the wavelengths of UV radiation. The commonly used source of UV radiation is hydrogen or deuterium discharge lamp, while a tungsten filament lamp is used for producing visible light. A monochromator which separates the radiation into individual wavelengths. The single wavelength of the radiation is split into two beams, one of which passes through the sample cell while the other passes through reference cell. A detector which continuously measures the intensity ratio of beams transmitted through the sample and the solvent respectively. A recorder chart paper which automatically records the absorption of light at each wavelength as a graph of absorbance versus wavelength. Principle of UV spectroscopy. Absorption of UV and ultraviolet light produces changes in the electronic states of a molecule associated with the excitation of an electron from a lower to higher energy level, but it may be noted that each electronic level in a molecule is associated with a number of vibration sublevels with small energy separation, and each vibrational level in turn is associated with a number of rotational sublevels with still smaller energy separation. Therefore, in its transition to higher energy level, an electron can go from any of the sublevels corresponding to various vibrational and rotational states in the ground state to any of the sublevels in the excited state. Appearance of broad bands and not sharp peaks in spectrum. If the electronic excitation in the molecules has occurred without any accompanying changes in vibrational and rotational sublevels, the spectrum would have electronic excitations. Electronic transition involves the promotion of electrons from one orbital to another orbital of higher energy level, a sigma electron, a pi electron, and an electron. The higher energy orbitals are antibonding molecular orbitals, which may be vacant in the ground state of the molecule. The antibonding orbitals associated with the sigma bond are known as sigma star orbital, and that is associated with pi bond is called the pi star orbital. Since the n electrons are not concerned in bond formation, there are no antibonding orbitals associated with them. The electronic transition taking place in the ultraviolet and visible regions are sigma to sigma star, n to sigma star, n to pi star, and pi to pi star transitions. First, pi to pi star transitions in which a pi bonding electron is excited to an anti-bonding pi star orbital are called pi to pi star transitions. And since these wavelengths are lesser than 200 nanometer and fall in the vacuum region, usual spectroscopic technique can't be used in such cases. Second, n to pi star sigma star transition. These are the electronic excitations from a non-bonding atomic orbital to an anti-bonding sigma star. And to pi star transition. These are the transitions in which an electron is a non-bonding orbital is promoted to an anti-bonding pi star orbital. Compounds having double bond between hetero atoms C double bond S and double bond N. Pi to pi star transition. The transition in which a pi electron is excited to an anti-bonding pi star orbital are called pi to pi star transition. Effect of conjugation. Conjugation of double bonds lower the energy required for electronic transition. As a result, molecule containing conjugated systems such as C double bond C, single bond C double bond C, and C double bond C, single bond C, double bond O. Transition probability. It is interesting to note that it is not necessary that exposure of a compound to ultraviolet or visible light must always lead to an electronic transition. On the other hand, the probability of a particular transition depends upon the value of molar absorptivity AMX and certain other factors. Accordingly, transition have been divided into categories. There are two types of transition. First one is allowed transition, second is forbidden transition. Allowed transition, these are the transition which have lambda max 10 raised to the power Emax 10 raised to the power 4 or more. The probability of the occurrence is very high. These are generally due to pi star transitions. Second, forbidden transition. These are the transition for which Emax is generally less than 10 raised to the power 5. They usually related to n to pi star transitions. Concept of chromophore and auxochromes. Chromophore. The term chromophore was originally used to denote a functional group or some other structure features, the presence of which imparts a color to the compound. For example, nitro group chromophore, since it is present in the imparts yellow color to the compound. And to pi star transition. Auxochromes. An auxochrome is a group which is Auxochrome is a group which itself do not act as a chromophore, but when attached to a chromophore, it shifts the absorption maximum towards longer wavelength along with an increase in the intensity of absorption. Some commonly known auxochromic groups are OH, NH2, OR, NHR, NH2. All auxochrome contain one or more non-bonding pair of electrons. Due to conjugation, there is a decrease in energy difference between the ground state and excited state of the group. Change in position and intensity of absorption. For isolated chromophore groups such as C double bond C and C triple bond C, absorption occurs in far ultraviolet region which can't be easily studied, but the position of absorption maximum and the intensity of absorption can be modified in different ways by some structural changes or changes of solvent. These changes can produce four kinds of effect. First, bathochromic effect or redshift, hypsochromic effect or blue shift, and third is hyperchromic effect. Fourth is hypochromic effect. First, bathochromic shift of redshift. It involves the shift of absorption maximum towards longer wavelengths. It can be brought about by three different methods that given by attachment of an auxochrome to the group. When an auxochrome such as a OH or NH2 is attached to a chromophore, it leads to the conjugation or helps in extending conjugation by conjugation of two or more chromophoric group. Bathochromic shift is also produced if two or more chromophores are present in conjugation to a molecule by using solvent of lower polarity It is possible to achieve bathochromic shift by using a solvent of lower polarity. Second, hypsochromic shift or blue shift. It involves the shift of absorption maximum towards shorter wavelength. It may be brought as follows: by removal of conjugation in the system. For example, protonation of alanine causes a blue shift from 282 to 203 nanometer. By using solvent of higher polarity, use a solution of higher purity can also bring about hypsochromic shift. Hyperchromic shift. This effect involves an increase in the intensity of absorption. Hypochromic shift. It involves a decrease in the intensity of absorption. Solvent effects and choices of solvent. Solvent effect. The solvent effect. The solvent used for dissolving a compound under examination has profound effect on the UV spectrum of the compound as given below. Effect on fine structure. As a result of interaction of a solute with the solvent, the fine structures of the absorption band is blurred and a smooth curve is obtained. The smooth curve out of the spectrum derives us to the much usefulness. The fine structure of UV spectrum is best observed in vapor phase. Effect of on the position and intensity of absorption maximum. Changing the polarity of the solvent may also lead to changes in the position and intensity of absorption maxima. Effect on non-polar compounds. In general, changes in non-polarity of the solvent do not cause any significant shift in the spectra of non-polar compounds such as dienes or conjugated hydrocarbons. For example, the absorption maximum for non-polar compounds is practically the same in alcohol. Effect of polar compounds. In case of polar compounds such as alpha, beta, unsaturated carbonyl compounds, the absorption maximum generally gets shifted with the change in the polarity of solvent. It has been observed that shifts are of two types: shift in the N to pi star transition, increase in the polarity of the solvent, shift N to pi star transition to shorter wavelength, that is blue shift. For example, absorption maximum of acetone is 279 nanometer in hexane, at 270 nanometer in ethanol, and at 264 nanometer in water. This shift towards the shorter wavelength is mainly due to the greater stabilization of the ground state than the excited state through dipole-dipole interaction, formation of hydrogen bonds, or solvation with the polar solvent. As a result, the difference in the energy between the ground state and the excited state increases, and the absorption towards shorter wavelength take place. More polar in the ground state. Second is shift in pi to pi star transition. Increase in the polarity of solvent shifts pi to pi star transition to a longer wavelength. For example, it has been observed that has compared to the solution in hexane, solution in ethanol generally shows the red shift of about 10 to 200 nanometer. For example, the molecule of ethylene is more polar in the excited state than the ground state due to greater polarity of pi star orbital compared to pi orbital. As a result, pi star molecular orbita will be relatively more stabilized by dipole-dipole interaction with the polar solvent as compared to stabilization of the ground state. Therefore, lesser energy will be required for such a transition, and the absorption will shift towards longer wavelength. Shift in N to pi star transition. N to pi star transition are very sensitive to hydrogen bonding. For example, alcohols and amines from hydrogen bonding with the solvent molecules due to the presence of non-bonding electrons on the heteroatom. As a result, more energy is required to N to pi star transition in the polar solvent, and shift towards lower wavelength take place. To sum up, if a group of is non-polar in the ground state, then the excited state increases the polarity of the solvent, shift the absorption to the shorter wavelength. If a group is more polar in the excited state than ground state, then the increasing the polarity of the solvent shift the absorption to the lower. Choice of solvent. First, it should be transparent in the wavelength region under examination. That is, it should not itself absorb radiation in the region being examined. Second, it should be less polar so that it has maximum interaction with the solute molecules and has no effect on the fine structure of absorption bands and the position of absorption bands. The most commonly employed solvent is 95% ethanol. It is cheap, has good dissolving power, and does not absorb radiation above 210 nanometer. In other words, it is